So what could be reasons for? Okay, what could be possible reasons for a half entangled state to be the one where you've got a controlled operation and the target qubit is superposed like relatively to the control qubit in a way that you're creating two different computational branches. One of them has the state 0 plus 1 and another one has the state 0 plus I1, I being the complex part of a phase, right? What would be, why is these different than like having the state 0 plus 1 and 0 minus 1 in two different computational branches, and these actually being a full, like a maximum entanglement? In terms of interference, like as I said, like if we're to think about interference, the maximum entanglement basically interferes. The maximum entanglement basically, like the two branches, they would have destructive interference in a way that they lose the superposition. This means, like, is it like that? Okay, so that could be, right? So there's maximum entanglement where both superpositions, both branches are such that, like, when, to be honest, like you could think of the fact that when, like, if you would interfere them, they actually come back to the original state, right? Like, let's imagine let's imagine that your initial state is, now that's not true because your initial state can be plus the plus state, and then you apply Control Z, and that kind of creates another branch which is like the 0 minus 1, and so then you have like maximum entanglement. But if you consider the two branches, it's clear to me, it seems to be at least clear to me intuitively that these branches are completely, or they are more opposite to each other than like with a non-maximum entanglement example, right? And so basically what this could mean, it's a difficult thing to think about, like if they would interfere, you would adapt with a non-superposed value. But I'm not so sure if this is something that always applies, because the other two, they basically have constructive interference. There's constructive interference between the branches. I mean, it's bad to say that there's constructive on one side and destructive on the other one, because it's not true. I mean, the other one has also the constructive, like the zero component has both a plus sign, and then so they constructively interfere, and then just the ones cancel out. But the difference will be that you're going into a non-like superposed state, and that's, I'm trying to relate these somehow to the notion of entropy, or maybe the notion of the information being spread totally across the branches. That's not true. It's not across the branches, but it's across the actual system. So yeah, but that actually is the branches, right? Like, because you've basically branched out. So you have a controlled Z, and so now your branches are kind of, if you think about the branches including the control, you've got one branch which is like, let's start from scratch. So you have two qubits. The control qubit is in the plus state, and the target qubit is in the plus state as well. And you apply Control Z. We know this creates, I mean, you can go ahead and try, this creates a fully entangled state. If you take a look at both Bloch spheres, they'll both be at the very center. So what this means is, like, you're creating, like, if you think about the two computational branches you're creating, basically one is the the branch where the target, the control qubit is 0, and so the target qubit stays in the plus state. So it's the plus state plus a 0, or times a 0. That's probably more appropriate. And that's one branch. And the second branch is the minus state times the 1 state. So that's it. Like there's no it's weird to say there's no more information anywhere else. It stays there. Whereas the example of, like, you apply a control S, okay, instead of a control Z. So what you do is you end up like with 2 branches. One branch is the one with the 0 in the control and a plus state of the target, so it's a plus times 0 part of your whole state. And the other one is the like 0 plus I1 in the target times 1 in the control. And so why is that different than the other example? Why is that entanglement weaker? Why isn't it maximum like in the other case? Because we have the 2 branches. It's gotta have to do something with the phase. And I suspect interference in this case, because it's really the only difference that I can actually see or think of. And I'm not even talking about the amplitudes, just the phases for the moment. So that's going to be trickier. It's going to get trickier actually. Maybe let's think about another example. Can we think about another example of what? Like of maximum entanglement or partial entanglement? I mean, these are the only... Okay, so let's think maybe something with amplitudes. So if you would think about 2 qubits, the first one is in the plus state, the second one is in the what? Like, say, in the, I don't know, 20% 0 and 80% 1, with no relative phase difference, and we apply a control knot. So what this turns into is a state where a system like 2 branches, one has got like a 0 in the control, a 20% 0 and 80% 1 in the target, so it's like 20% 0 and 80% 1 times 0, and then the other one has a 1 in the control, and then it has the probabilities flip, right? So it's going to have like an 80% on the 1 side of things, and a 20% on the, an 80% on the 0 and then a 20% on the 1. That's messy. Without writing it down, it can be a bit confusing, so bear with me with this. You can try to write it down if you want. Good. What is this entanglement? Like if I were to imagine that those 2 computational branches interfere, they both have the same relative phase, and so I kind of think that intuitively we should be getting a 50-50. It's like a 50-50 superposition, because they will normalize, like the 20 adds up with the 80, so it's like 100%. The 80 adds up with the 20 on the other side, so it ends up at 100%. But those things normalize, and so they end up at like 50% each. So you would end up with an equal superposition, to be honest. And so according to my example or my reasoning until now, that would be that this is like non-maximum entanglement. Like this is not like because you still have a superposition, so they don't like interfere away and you lose the superposition. Because that's my current way of thinking. But I really have no idea how to calculate data on my head. Like I really have to go to query to check that out. And I think I'll probably do that and see whether that's true or not. Actually, because I'm recording this on the phone, I'll pause for a second, go check and let you know. So it's good that at least I have the phone on me. Okay, so I'm back. It actually works. Like if you say the target qubit is initialized in the state, like, do like a quarter turn of an X gate, like X to the power of 1/4, and then like apply an S gate because you want to correct the phases, right? Like you want the phases to be, like you want the relative phase to be 0. In this case, you want the relative phase to be 0. Why? I don't know. I think it's going to be easier for me to reason. Because if you don't apply that S gate, then you have like, after applying an X to the power of like 1/4, you're getting a complex phase on the one component. And if you don't have this S and then you apply a control X to the state, like and the control is on the plus state, then you actually get full entanglement. But if you correct for the phase, like if you add like an S gate after the X, after the quarter X gate, then you actually don't get like, you don't get actually, well, give me a second. Sorry, some some technical problems. You don't get you don't get full entanglement. I think you also don't get like half entanglement, right? So what happens here is, I think you do get into a 50-50 superposition for the target qubit, but it still bothers me that like Quirk can't tell you what the phases are because of the entanglement, I guess, but I really don't know why. And you still see the probability being 50-50, right? Which is intuitively what I said. Like if you've got like an 80-20, and it was not an 80-20, like if you do a quarter of an X gate, you get like something like 85 or 83%, I think. But whatever, like what matters is that the control X kind of flips that on the other branch. And so if you would imagine putting the two branches together, you get a 50-50. And it's actually, it is what happens, to be honest. Like if you get a 50-50%. So it seems like there is this notion of interference between the branches to some extent here. Like it's not clear to me, but in this case it's not fully entangled. So what I was saying is it's fully entangled when the two branches will basically go to a non-superposed state. But I think that I just proved myself wrong, because if you don't add the S gate that I talked about, I think you still get into a 50-50%. But then it's a fully entangled state, so that's kind of I think that's not the right path. Okay. Well, where can I like flip this around and think about it differently? So something funny happens when there's complex phases. This I just see now. There's got to be something with the interference between branches, because obviously the case that's easy to understand is when there's no entanglement, regardless of the fact that you've applied a control NOT gate, which is an entangling gate. Sometimes there's no entanglement, and the reason is that the two computational branches you end up with, they are equivalent, and so so there's no sense in them existing separately. Yeah, so that's obvious. But then the entanglement versus max entanglement versus non-max entanglement, there's got to be some relation there that's got to do with the type of interference that we see between the branches, if there is such an interference. I don't know. It's more complicated than I thought.